Hello, everyone. We are very happy to have Professor Yvonne Loseu from Yale University. He will talk about quantizations in Lie representation theory.
Okay. All right. Yeah, I should say it's been a very interesting conference, and I've learned a lot of things. So, thanks the organizers for having me. And the title of this talk is Quantizations in Representation Theory, which on its own is a huge subject in many parts. And I'm only going to talk about one of them, but the one which was historically first. And it's motivated by the study of unitary representations. It's a very classical subject in Lie representation theory, although unitary representations in this talk are just for motivation only. Okay? So the second part is about quantizations and their representation. It's a main part of the talk. And if I have time in the end, I'll talk about unipotent representations and connections to symplectic biology. Okay? And in fact, there are some references just, for the purpose of giving reference. Okay. So let me give just basic definitions concerning unitary representations. I start with a real Lie group, G sub R. And I care about its topological group representations in Hilbert spaces by unitary operators. That's what I mean by unitary representation. And they're completely reducible. Irreducible representations are those without a proper closed G-stable subspace. And of course, the basic question is to try to classify these representations. So, to start, let me, and I care about semisimple groups. So let me just give you some standard constructions regarding semisimple Lie groups. G sub R is going to be a semisimple group over R. You can consider SLN R or SLN C. It's a complex Lie group which can be viewed as a real one. Then I can, of course, consider its Lie algebra. And I can complexify it. Consider Lie algebra over C. For example, for SLN R, I will get SLN C. But for SLN C, I will get two copies of SLN C. Okay? And then in every real Lie group, I have a unique up to conjugacy maximal compact sum. For SLN R, it's SON. For SLN C, it's SUN. Then I can again complexify this group and consider its Lie algebra. That this funny symbol is what I think German K is. Okay? So in the first example of SLN R, I will get SON C. And then in the second example, well, my Lie algebra is two copies of SLN C. And the Lie algebra of K is one copy of SLN, which is embedded diagonal. Okay? And then an important object in this business is the orthogonal complement of a K inside of G. For example, if I do SLN R, then K perp is just all symmetric matrices in SLN. Okay? So next I want to discuss two ideas in the subject which are completely fundamental. And the first one is due to Harish-Chandra. And the idea of Harish-Chandra is that to study unitary representations, which involves functional analysis, you want to translate this problem to the language of algebra. So that's why I call it algebraization. And so the U of G is going to denote the universal enveloping algebra. And then in the series of work in the 50s, Harish-Chandra defined what is now known as Harish-Chandra GK module. So remember, so I have this notation here. So G is a complex Lie algebra, K is its symmetric sum. So what is the Harish-Chandra GK module? It's a module over U of G together with an action of this group K. And I want the compatibility that the two actions of the Lie algebra coincide. First, my Lie algebra sits inside of G, and so I can just restrict the action of G to K. I get one action. But then I also have an action of the group K, so I can differentiate this action. And I get the second action of the Lie algebra. I want them to coincide. in some parts of the field. This is called strongly equivariant GK model. Okay? Now, here is a special case, and it's a case when GR was actually complex group, like SLNC. It's different in many respects from the purely real case. So what happens in this case is that, well, my complexification of the real Lie algebra G is just 2 copies. And a modulo over G times G can be actually viewed as a bimodulo over the universal enveloping algebra. So I have this U of G bimodule B, and the condition of being Harish-Chandra can be interpreted as follows. I can consider the adjoint action of G on B, just by the usual formula for the commutator. And I want this action to integrate to the group. Okay? That's how I get this action of K, which in this case is G, on the bimodule. So Harish-Chandra bimodule is a bimodule over the universal enveloping algebra where the adjoint action integrates to the group. And the most basic example you can imagine is U of G itself. So here the adjoint action integrates, classical result. And in this case, I will use term Harish-Chandra bimodule. A special case of Harish-Chandra. All right, so what does it have to do with unitary representations? Harish-Chandra gave the following definition. He said that GK module is unitarizable if it comes with a positive definite Hermitian form, which has the following invariance property. I want the action of the real part of my Lie algebra to be by skew Hermitian operators. Like you should think about this as follows. So your G acted by unitary operators. So you would kind of expect that its Lie algebra acts by skew Hermitian operators. And then there is the following theorem due to Harish-Chandra, which says that unitary representations of G sub R, the real group, are in initial bijection with a reducible unitarizable Harish-Chandra GK model. And so the way how it works, you start with a unitary representation, and you take something which you should think about as locally finite part. So an example will be something along the following line. So imagine that your Hilbert space is L2 of the circle, and then its locally finite part is just polynomials in the exponential function, like polynomials in Fourier modes. And then, if you want to start with a irreducible, unitarizable Harish-Chandra GK module, then you need to complete in a suitable sense. You will get a Hilbert space. And these two operations are inverse to each other. And so, thanks to this, we no longer need to care about this side. It's kind of functional analytic in nature. We can care about this side, which is algebraic in nature. And we know a lot about irreducible Harish-Chandra modules. They're classified in various ways. And moreover, with at least some of the specifications, it's easy to say when such a module has an invariant Hermitian form, which may or may not be positive definite. So that's an easy part. And then the difficult part really is to determine when is this form, which is unique up to scaling, is positive definite. So that's a really subtle part of this question. It's kind of the answer is not known up to this point. So that's kind of that's the work of Harish-Chandra in the 50s, and then the second basic idea in the subject that I want to talk about was discovered by Kirillov now in the 60s. And so the idea of Kirillov explains how and why the word quantization is relevant in this subject. So first, let me tell you the result that Kirillov proved, and the result is known as the orbit method. So I consider the adjoint representation of the Lie group G sub R on its Lie algebra, and of course I can dualize and consider the coadjoint representation. And then I can consider the orbits for this representation. Okay, that's some set. And what Kirillov tells us is that if our group is simply connected, well, that's a fairly mild restriction, but the important restriction is that it should be nilpotent. So if my group is simply connected and nilpotent, then I have a natural bijection between the unitary representations of G sub R and coadjoint orbits. Now, that's the good news. Somehow the bad news is that there is zero chance that this carries over to semi-simple groups, and you already see it in the case when the group is compact. So what happens when the group is compact is that every irreducible unitary representation is finite dimensional. And of course, we know how to classify a reducible finite dimensional representations. They're classified by chi-squares weights. In particular, that's a countable set. If you think a bit about the set of orbits, that's in bijection with all dominant real weights. It's an uncountable set. So there is no bijection whatsoever. Okay? And kind of for the general semi-simple group, the situation gets even more subtle. I mean, the cardinalities, of course, are the same, but the structure is completely different. And we don't know any precise analog of orbit method in the real semi-simple up to this point. So that's the result. You can ask, okay, so what does it have to do with quantization? What is it that we quantize? So for this, let me remind you the definition of Hamiltonian manifold. And the Hamiltonian GR manifold is a triple consisting of X, which is a C-infinity manifold, a symplectic form, omega, which is supposed to be invariant under the action of the group. And then the set ingredient is a moment map. It's a map from my manifold to the dual of the algebra, which by definition is GR equivariant and satisfies some condition on its differential that I'm not going to give. Okay? That's a right notion of symmetry in symplectic geometry. So let me give you a couple of examples, and we'll start to see how this is relevant for our business. So if you have a coadjoint orbit, GR applied to some element alpha, you can define on this orbit the so-called Kirillov constant form. I won't need the construction. But that's an invariant symplectic form, but then the moment map is very easy to describe. My space is an orbit inside of G dual, and so I can just take the inclusion. Okay? That's a basic example of a Hamiltonian map. And you can do a bit more general construction. So if you take a subgroup inside of the stabilizer of my element alpha, I can consider, of course, this concept, and I want it to be discrete. In other words, I want this H, the subgroup, to contain the connected component of the stabilizer. What does it give me? It gives me, of course, I have a map from GR quotient by H to the orbit from the inclusion of the stabilizers. But my condition that this coset space is discrete tells me that my map is a cover in the sense of topology. In particular, I can just pull back the symplectic form from the orbit to the cover and get a symplectic form there. And then I just compose the inclusion of the orbit into G star with a projection from X to the orbit, and I get a moment. So that's slightly more general class of Hamiltonian manifolds. And you will notice that the common feature of this Hamiltonian manifolds is that the actions are transitive. All these manifolds are single orbits. All these manifolds in the signal. Now, there are two observations. First of all, there is kind of an easy exercise which says that every transitive Hamiltonian action is of this form. It's an action on an equivariant cover of a coadjoint orbit. But the second observation, which is a very nice exercise in like basic Lie theory, it's not completely trivial, tells you that if the group is nilpotent, then actually every coadjoint orbit is simply connected. And you don't get any proper equivariant covers. So, if you look at Kirillov's statement, Kirillov's statement here, then kind of the one side of his bijection is just Hamiltonian manifolds with transitive action. And here comes quantization, namely the most classical version, geometric quantization. So what geometric quantization seeks to do, it seeks to relate like the classical world and the quantum world. In the classical world, like our phase spaces are symplectic homogeneously Poisson manifolds. In the quantum world, they are Hilbert spaces. And you seek to establish some kind of correspondence, and you want your correspondence to respect symmetry. If you have a Hamiltonian action on a symplectic manifold, you expect that on the corresponding Hilbert space you will get a unitary representation. And there you can get very optimistic and says that, in the classical world, the condition of minimality perhaps means that the action is transitive. Well, in the quantum world, the condition of minimality perhaps means that representation is reducible. And so you would kind of guess that, transitive Hamiltonian actions are just in bijection with reducible unitary representation. And it somehow miraculously works for nilpotent groups. And then kind of this optimism ends because kind of for more general groups, for example, for semi-simple ones, this doesn't work. It's just too naive. And so that's kind of was the story about unitary representations. Are there any questions? All right. So let me get to like the main, if you can say algebraic, algebra geometric part of this talk. And talk about quantizations and their representations. And starting from now, what quantization means, the field of quantization. I will explain what this means in several. So, I start with A, which for me is a finitely generated commutative algebra over the complex numbers. And I wanted to come equipped with two additional structures. I wanted to be graded by negative integers, so that the degree 0 component consists of scalars. Okay? And I wanted to come with a Poisson bracket, which I denote by this curly bracket. And I want these two structures to be compatible in the following sense, that when I take homogeneous element of degree I, homogeneous element of degree j, the bracket has degree I plus j minus 1. So the bracket decreases degrees by 1. Okay? So what are examples of this situation? Well, the most basic one, you can take a finite dimensional algebra, G, and consider the symmetric algebra G. This has a unique Poisson bracket, which on the elements of G itself coincides with the Lie bracket. And this, of course, has degree minus 1, as we want. So now let's kind of get closer to what we are going to study, and that's example 1. I want to take a semi-simple algebraic group, G, over the complex numbers. And then, of course, I can identify its Lie algebra, small g, with its dual via the killing form. Particular, an orbit in G is the same thing as an orbit in G dual. So let me pick an orbit G. That's, of course, a smooth symplectic variety with constant Kirillov form. Therefore, the algebra of global functions inherits a Poisson bracket. Then it's not such a difficult exercise to show that this algebra is actually finitely generate. There is something to prove because this O is not a phi, it's only quasi-phi. But nevertheless, this is the case. And then you can ask, for which orbits is this algebra graded? So what I want is a graded algebra. So when is it graded? And here is a nice, this has a nice answer. This algebra graded for nilpotent orbits O. So what is a nilpotent orbit? There is a motion of a nilpotent element in any semi-simple Lie algebra, and if your Lie algebra is classical, then it just means that this is a nilpotent matrix. Of course, this property is stable under conjugation, and so we can talk about nilpotent orbits, meaning orbits of nilpotent elements. Okay? So for classical Lie algebras, we just get nilpotent conjugacy of matrices. So why is it graded? Well, if I take an element of my orbit and a scalar, which is not zero, then the product is still in the orbit. It's an easy exercise. And therefore, I get an action of the multiplicative group on O, which then gives me a grade. And this grading has the property that the Poisson bracket has degree minus 1. So that's one class of Poisson algebra that I'm going to care about. And let me give you a baby special case, which is a basic example. So, It's a colloquium talk. Every colloquium talk should have a joke in it. And the joke is that, like, for, what is the difference between Russian representation theory school and American representation theory school? So for Russian representation theory school, the basic example is SL2, and for American representation theory school, the basic example is EH. So we'll do Russian tradition and consider SL2. I hope nobody objects. So let's take SL2, and the only interesting important orbit is just the non-zero one. It's all important matrices of rank 1, and that's how they do it. So, there is condition that it's non-zero, and there are polynomial conditions saying that the determinant is 0. Okay? So what is the algebra of functions? Well, I take polynomials in 3 variables and mod out this relation. That's a quadratic column. It is graded, where the degrees of the variables are equal to 1. How do I define the Poisson bracket? Well, there are several ways. One of them is just to observe that this algebra is embedded into polynomials in 2 variables by the following formula. So a goes to xy, b goes to x squared, c goes to minus y squared. This relation is obviously satisfied. And then the algebra of polynomials in 2 variables has a natural Poisson bracket, which is that's the first bracket that a person sees in their life. It looks like this. And then you just notice that the subalgebra generated by these elements is stable under the bracket. Okay? So that's a concrete example. Let's continue. This example again has generalization, and this has all right. Okay, so it has generalization along the lines of the previous story. So my orbit is of the form G mod H for some algebraic subgroup H, and then what I can do, I can take a subgroup of finite index. Let's call it H0. It's the same as to say that the quotient is discrete. And I can consider the corresponding cosset space, which is an equivariant couple, and still take the algebra of regular functions. It's still Poisson, it's finitely generated, and it's graded. There is a little subtlety here, and it's that if I want to have the degree of the Poisson bracket to be -1, I need to grade by 1 over 2z. But let's ignore this. Let's see. Yes. Oh, no, not that. Wait, right. So here is again a baby case of this construction in the case of SL2. So I take the same nilpotent orbit O, and I compute the stabilizer, which is, the stabilizer, which is this. So it's like a semi-direct product of strictly upper triangular matrices with Z mod 2Z. And of course, there is an index 2 subgroup here, H0. I can take the corresponding quotient O tilde, and this is C2 without 0. Okay? And then I take polynomial functions, which has a standard Poisson bracket. And I need to put degrees to be 1 over 2. Okay? That's another example. And so in what follows, O is always going to denote an important orbit, and O tilde is going to denote the problem. So now, okay, I need to talk about quantizations. And these are going, for me, they're going to be like filter quantizations. So let me explain what this is. I have an associative algebra with algebra filtration. Let me call it curly A. So here is a filtration. And I want the condition that the degree of Lie bracket is less or equal than -1, parallel to what I had for Poisson bracket. Then, as usual, I can form the associated graded algebra. And this condition tells me 2 things. So first of all, it tells me that this algebra is commutative. Okay, because the top degree of the commutator died. But then I can consider the degree -1 component of the commutator, like so, and it gives me a Poisson bracket of degree -1. So now I can define fielded quantizations, and what those are. So I start with a graded Poisson algebra A, and the fielded quantization is a pair of the fielded algebra curly A and then identification of its associated gradient with straight A, which I want to be compatible with all structures that I have, which is grading and Poisson grading. Okay? So informally, we can think about this as follows. So we want to quantize, meaning deform the product, and we want to do it just by adding lower degree terms. We still want to have it associative, and when we do so, such deformation gives rise to Poisson gradient. And of course, we want it to coincide with the initial gradient. So let me give you some examples. So example number 0 is that the universal enveloping algebra is a quantization of the symmetric algebra. And the isomorphism between the associated gradient and the symmetric algebra is just Poincare-Bergov-Witzel. So now, getting closer to the setup that we want to pursue, let's again consider semi-simple algebra G, and then inside we can have the nilpotent cone, which I call curly M. Okay? It is acted on by G, and there is an open orbit called principal. For example, if you do SLN, that's just an orbit of all matrices whose Jordan form has a single block. Then, okay, so how do I construct quantizations of this algebra of functions, which is the same as functions of the nilpotent cone? For this, I use the theorem of Harish-Chandra, which tells me that the center of the universal enveloping is the same as Weyl group invariant functions of the dual of the cartan. And so in particular, if I have a point in H sum of W, let's call it lambda, I can consider the corresponding maximal ideal in the algebra of invariants, which is the same as the center. So I can consider this maximal ideal as sitting inside of U of G. And I can form this left ideal U of G times M lambda. Since M lambda is central, this ideal is two-sided. And I can take the quotient. So this gives me an algebra. It comes with a filtration, which satisfies all the properties that I need. And with a little work, one can show that this quotient is actually a filtered quantization of C of M. So what I get is not a single filtered quantization, but a family parameterized by this space. Okay? So let's do like a baby case. Yeah. We'll get there. We'll get there in 2 minutes. It does. So what does it give me for SL2? Well, the center is generated by Casimir element, which I want to slightly denormalize like so. H plus 1 squared plus 4FE. And then my A lambda is just U of SL2 mod out the relations that C is equal to lambda squared. The lambda is an element of H star, which is identified with the complex numbers. Now let's do a baby example number 2, where my O tilde, that's a typo, is C2 without 0. Of course, the algebra of functions is polynomials in 2 variables with standard bracket. And it has unique quantization, which is the Weyl algebra. Obtained as follows. I take like non-commutative polynomials in 2 variables, and I mod out the relations that the commutator is equal to 1. Okay? So I gave you these definitions, but then kind of you can ask, why should we care about this setup? What does it have to do with our original problem? And so here is what. So notice that O tilde, well, it has moment map to G star, which by considering pullback gives me a map from S of G to the algebra straight A. And that's a G equivariant homomorphism of graded algebras. I can then lift it to a filtered algebra homomorphism from U of G to the quantization curly A. For example, in the case of principal nilpotent orbit, A lambda was just a quotient of U of G. And so this quotient map is just the map that I need to consider. And so the point here is very simple. So if I have a module over A, then it automatically becomes a module over U of G. Okay? So if I understand the representation theory of this quantization, I will get some information about the representation theory of my algebra G. So then the roadmap is the following. First, I need to classify all possible filtered quantizations for these algebras. And this is completely done. Then I want to classify some nice modules over A. And I will try to explain what I mean by this. And somehow the whole, well, I mean, here's the name, which I will explain closer to the end of the talk. This module should be thought of as quantizations of singular Lagrangian subvarieties. And then one could hope that these quantizations of singular Lagrangians will contain all unitarizable Kharish-Chandra GK modules, at least in the case when, well, in the case when GR is quasi-split. This includes, for example, all complex forms. And this classification is done to some extent. And then that's kind of the number 3, the hardest part, is to decide which modules obtained in 2 are unitarizable. And this little is done about it, but something important is done. If I have time, I will report on it. All right, so I'm just going to follow this roadmap and first tell you about classification of field of quantizations. So I start with this algebra of functions on a cover of an important orbit, straight A. And then there is a following theorem due to myself in 2016, is that I have a finite dimensional vector space, which I call H sub A, and a reflection subgroup, W sub A, in the group of linear transformations, such that fielded quantizations up to isomorphism are parameterized by points of this quotient. And when I write this, I just mean the usual quotient. So this is in particular an affine space. Okay? And so how does this work in my examples? Well, if A is functions on the nilpotent cone, and this H sub A is just the dual of the cartan, and W sub A is Weyl group W, and I recover the construction in the previous example. So in particular, this exhausts all quantizations. Now, baby example 2 is a bit silly because in this case, H sub A is just trivial. And I have only one quantization. So here is a remark. Well, it's one and only group acting on zero-dimensional space. It's a very special group. So I want to say a couple of words of how this quantization works, and this involves some well, maybe by now not so recent advances in variational geometry. So what we can do, we can consider the corresponding affine variety X. And the important fact is that X is singular symplectic in the sense of body. So it's as symplectic as a singular Poisson variety can be. So now, if you have a singular variety and you have variational geometry, you try to study maybe resolutions of singularities, maybe partial resolutions. And in this world, you care about like in every world, you care about Crepant resolutions, but in this world, Crepant becomes Poisson. So you want to get a Poisson variety so that the resolution morphism is still a Poisson morphism. And the very important fact, which kind of originates in the famous work of Berker, Cassini, Heiken, and McKernan, is that we have a maximal partial Poisson resolution in this case. Let me call it X tilde. For example, if your X is an important cone, then the construction is very classical. It's just a Springer resolution. And in this case, the variety is smooth. In general, it's still simple. Now, Yep. So then I can obtain this H sub A as a second cohomology of the smooth locus of X tilde. And from such a parameter, I can produce a fielded quantization, in some sense, of the structure sheaf of X tilde. And I denote it by d lambda t. For example, in the case of Springer resolution, you just take sheaves of twisted differential operators, which are very conveniently parameterized by points of H star. Now what I can do, I can take the global sections. And I obtain all quantizations, but an important feature is that different quantizations can have isomorphic global sections. And this happens if and only if the two parameters are conjugate by this platform. So that's a classification result. And then I want to just kind of explain a funny consequence of this classification, which is some version of the Kirillov orbit method. So Kirillov orbit method is a bijection between two kinds of orbits, like classical orbits and quantum orbits. And it turns out that, well, as I explained, on the level of unitary representation, this fails badly. But in this algebraic setup, it works perfectly well. Namely, we can consider the following two sets. So I consider all coadjoint orbits, and I take all possible covers. In other words, I consider all possible transitive Hamiltonian actions. That's kind of the same thing as Kirillov has in his theory. But that on the quantum side, I just take all fielded algebras that I can obtain. And my fielded algebra just comes as quantizations associated to arbitrary equivariant covers of arbitrary nilpotent orbits. So I take all of those, and I consider them up to G equivariant fielded isomorphism. And so these are all quantum objects that I get, and so it's kind of algebraic counterpart of what Kirillov has in his theorem. And it turns out that those two are in nature bijection.
Just to understand, so filter quantization, this only condition makes some discrete subset of this non-countable with what before, right?
Wait, filter quantizations are uncountable because they're parameterized by points of vector spaces. Essentially.
You need to have some discrete like weights, right?
No.
In some way,
Nope.
okay.
No, but that's on the level that's on the level of unitary representations, and I'm not doing that. I'm doing the algebraic setup where which you can rightly call symplectic. And so here's a bijection, and the way how it works is that the set A actually has a description very similar to set B, but instead of fielded quantizations, I need to consider fielded Poisson deformation. And that's kind of that these two sets of bijection is kind of a general pattern in all this quantization. That's one remark. The other remark is that, of course, here I can consider equivariant covers of nilpotent orbits. It's a part of set A, and you can ask where it goes in the set B. Turns out that it goes to quantizations with parameter 0, which can be called canonical quantizations. And that's going to be important later if I ever get there. Get some random quantization. No, I mean, you can compute what it is. I mean, it's not a problem. I mean, but it's nothing particularly good about it. All right. So now, okay, so this was part one of the roadmap, classifying algebras. Now I need to tell you something about their representation. So I start with some cover O tilde of an indifferent order, and the quantization parameter log, get an algebra, A lambda, and it comes with a homomorphism from U of G. What I can do, I can consider the kernel, which I will denote by I sub lambda of O tilde. And I want to make some simplifying assumptions. And the status is that what they simplify is a statement of results. So we have the same results in general, but they're more complicated to state. Well, I should say similar results. So first, I want this map from U of G to A lambda to be surjective. And second, I want the kernel to be a maximal ideal with respect to inclusion. This kind of can be checked at least in some cases. For example, if your lambda is 0, meaning we are talking about canonical quantizations, and O tilde is a Galois cover, meaning that the quotient of O tilde by its automorphism group is the original orbit O, then this assumption is false. And this kind of theorem, which requires a lot of work. So if you want to get to exactly these conditions, you need to do some work. Okay. So now, what I can consider, thanks to these conditions A and B, are Harish-Chandra A lambda K modules. And so what does it mean? It means I consider Harish-Chandra GK modules, which are annihilated by this ideal I lambda of O tilde. And I can talk about Harish-Chandra A lambda by. And so so there is still notation on this board, so maybe let me move slightly. And then one can ask how to classify these objects. So here is the first result due to myself in 2018, is that there is a normal subgroup, which I will call gamma sub lambda, inside of the fundamental group of my orbit, such that this category of Harish-Chandra A lambda bimodules is equivalent to the category of representations of a quotient as a monoidal category. Okay? And one can actually compute this gamma lambda explicitly, which I'm not going to explain. And so how to think about this result? So of course, representations of the fundamental group is the same thing in this case as local systems on the orbit. And if you have a Harish-Chandra A lambda bimodule, well, that's a quantum object. You can try to take the quasi-classical limit and ask what you get. In particular, what you get is a local system on all. This sort of is not a functor. It depends on some choices, but the observation is that this can be upgraded to a functor. So there is a functor going from this category to the category of local systems. And this functor is an equivalence, well, onto this subcategory. Okay? So that's how the classification works in this case. So let me give you some examples and also kind of, which can give you also some idea of how this works. So if I take a principal nilpotent orbit, and I take the canonical quantization lambda equals 0, then gamma lambda is just pi 1 of O, and the category of Harish-Chandra modules is just the category of vector space. Now here's an example which is more fun. So let me take G equal to SL2, or still consider the principal orbit, but now take the parameter 1 over 2. There is something very special happens for this particular parameter, and it's the following. I can construct my quantization A lambda as invariance inside of the bial algebra, A tilde, which is quantization of the cover of the orbit. So for the fundamental group is Z mod to Z, I'm going to act on this A tilde just by changing the sign of the generators. Okay? And then it turns out this A1 over 2 is just the invariance for this action. But now I can have a functor from representations of Z mod to Z into the category of Harish-Chandra bimodules. I do the following. I just essentially take the corresponding isotypic component inside of the algebra A tilde. And this will give me a Harish-Chandra bimodule. It turns out that this functor is an equivalence of categories. And this works like more generally, you know, if you're A lambda, nope, it's just a universal constant 1/2. No, I mean, so this is a general construction. If your A lambda is represented as invariance in some larger quantization, then you automatically have a functor from rep gamma to the category of Harish-Chandra bimodules over the invariance. And that's actually that's one of the ingredients how the theorem is done. All right, so that's the case of bimodules, which is kind of vanilla. And then there is a more difficult case of Harish-Chandra modules for the real ones. So that's more complicated. So I'm going to assume that G is simple. My K is a symmetric subgroup. So just as K on the board. And I want to impose now an assumption which is restrictive. I want to take the cover which is an orbit, so trivial cover. And I want to assume that the codimension of the boundary is big or equal than 4. A little bit later, I will give you some idea why I want this assumption. And here is a theorem from last year, due to myself and showing you, that under the assumptions that I've made, so there was the assumption that, that the map from U of G is surjective and the kernel is a maximal ideal. These are assumptions A and B. And then I also have this additional assumption. Then irreducible Harish-Chandra modules are in bijection with irreducible suitably twisted local systems on this intersection of O with K part. It's kind of the same mechanism as in the previous theorem. We actually have a category equivalence. So which twist I take will depend on quantization parameter. For example, if the quantization parameter is 0, the twist is half canonical. An important remark is that this intersection is actually a finite union of K orbits. And each of them is a Lagrangian submanifold inside of O. In the usual sense, it's smooth. And it's kind of the same argument as in theorem 1. I don't get the question. Yeah, I mean, it's just kind of, it's like a singular support of each of these modules is irreducible, and I pick that support. Okay? So these are theorems, and now I want to just put them in some general framework. So what I'm really doing here, I'm doing quantization of singular Lagrangian subvarieties. And one thing that I don't know about the subject is kind of a precise definition of what I should mean by a singular Lagrangian subvariety. So I have my singular symplectic X, this spectrum of functions on the orbit, and inside I can consider smooth locally closed Lagrangian subvarieties. For example, the bimodule case corresponds to the following singular symplectic variety. It's X times X opposite, and opposite just means that I consider it with opposite Poisson bracket. The diagonal embedding realizes O as a Lagrangian submanifold inside of it. Or I can take the real case and consider just O intersected with K part. It also gives me a smooth Lagrangian submanifold. And kind of both theorems, what they want to do, they want to relate this Harish-Chandra modules or bimodules, quantum objects, with some twisted local systems on these Lagrangian subvarieties. Now, the crucial observation that makes the classification work is that in both cases, the codimension of the boundary of the closure is actually big or equal than 2. For example, in the bimodule case, my y is just the same as x. X is singular symplectic, in particular normal. For a normal variety, the singular locus has codimensions. And so what we need to do, we essentially need to understand the geometry of this singularities to codimension 2. That's how the proofs work. That's kind of geometric in some sense. So then one can, of course, pose a general problem. Well, assume that we know what we should mean by singular Lagrangian subvarieties and singular symplectic X. We should try to quantize the subvariety together with some additional data. And at this point, it's not quite clear to me what this additional data should be. When the codimension of the boundary is big or equal than 2, the additional data is a suitably twisted local system. And in the general case, it should have some contributions from codimension 1 struct. And it's not clear what those contributions should be exactly. In this generality, this is known for the bimodule setup, where I take X times X opposite for my symplectic variety. My quantization is a product of A lambda with A lambda opposite, and Y check is X diagonal. And the answer is literally the same as in the least theoretic case. And I should say that this codimension 1 case is really challenging and complicated. So it's not clear what to do in that. Okay, that's the second part of the talk. Are there any questions? Mm-hmm. It just it's completely, it's completely agnostic of local systems being possible. So what this function does, roughly speaking, it micro-localizes to the open part, and then kind of observes that this kind of quantized local systems is just the same as possible. Which is something you can believe because the category of local systems is very vanilla, it's semi-simple, finitely minor simple objects. Great. Okay, so that's the last part, and it's about unipotent representations in symplectic biology. So here is the definition that we gave in our paper with Mason, Brown, and Matvievsky. We define unipotent ideals inside of the universal enveloping algebra as just kernel of the map to a canonical quantization of some color. So canonical quantization is one with parameters 0. Okay, so what do we get for the baby case of SL2? There are 3 covers. There is orbit 0 with non-trivial covers. The ideal is just the augmentation ideal. For the O principal unipotent orbit itself, we get U of G times the Casimir. So here is my version of the Casimir. And for its cover, we get U of G times Casimir minus 1 over 4. Just a go. And it turns out that all such ideals are necessarily maximal ideals with respect to inclusion. So then we can talk about unipotent representations, and there are two separate definitions. There is a general definition of unipotent Harish-Chandra bimodules. It's just Harish-Chandra bimodules of the quotient of U of G by a unipotent ideal. And then there is a less satisfactory definition for general Harish-Chandra GK modules. We need to start with a situation when the codimension of the boundary is bigger or equal than 4, and we can define what it means to be a unipotent Harish-Chandra module associated to this cover O. And it's just a module annihilated by the corresponding unipotent ideal. And currently, we don't know a general definition of unipotent GK module. What is clear is that all such modules should be annihilated by some unipotent ideal, but there should be some other conditions which we don't know at this point. And it all looks kind of arcane. It's not clear why should we concentrate on this object, as opposed to maybe some modules or bimodules or more general quantizations. So here are some reasons. So here is a kind of idea, here is a theorem which is work in progress of Dougal Davis and Lucas Mason Brown, is that all unipotent Harish-Chandra bimodules defined above actually unitary. So that's kind of, so I mentioned for you like 3 steps in the roadmap. That's essentially the only result we know about step 3. And this kind of it's essential ingredient is action between Hodge structures and unitarity, which was established by Davis and Below. Yeah. Positive definite. Okay, so that's a nice result, but then it kind of, there is also an expectation which was phrased by Vaughan in the 80s, is that kind of unipotent representations in this world should play kind of the same role as unipotent representations of finite groups have. And basically, we should hope that every unitary representation is obtained from a unipotent representation by 2 operations. So first, there is unitarity preserving parabolic induction, which for bimodules is a very easy operation. You just parabolically induce. And then there is a more subtle operation, taking complementary series. Complementary series tells you that, if you flatly deform your module in such a way that it carries a continuous family of Hermitian structures, then in some region in deformation parameters, this structure is still positive definite. And it's kind of the question is, okay, so what is the region? And so currently we try to work on this expectation in the bimodule case, and we have some conjectures of what is happening. So there's kind of motivations from the point of view of this theory, but then there is also motivation coming from somewhere else. And that's this connection with symplectic duality, which kind of Hirako Nakajima and to some extent Sasha Braverman explained in that. So this again goes back to this old work of Barbash and Vaughan, which was inspired by ideas of Arthur and like unipotent Arthur parameters and so on and so forth. So what they defined are so-called special unipotent ideals. And then they can talk about special unipotent Harish-Chandra bimodules or modules, but just by imposing this annihilator condition. So what are those? I won't tell you. I will tell you that their definition looks very different from what I gave you like 5 minutes ago. And what happens is that they start with an nilpotent orbit, but this nilpotent orbit lives in the Langland's dual algebra. And then from this orbit, they produce a very explicit maximal ideal inside of U of G. So maximal ideals are specified by the highest weights of modules that they annihilate. They produce a very explicit highest weight. So here is the theorem. In fact, all of their ideals are sum of ours. And the way how it works, I start with this O check, an nilpotent orbit in G check, and I produce d tilde of O check. It's a cover of an orbit that Barbash and Vaughan defined in that paper, in some way. And then we can explicitly describe this d tilde. So now there is a generalization of this construction due to, well, all of my co-authors that I've mentioned, which I'm not going to explain. And what does it have to do with symplectic duality? So what is the symplectic duality in very, very rough terms? So it's kind of a duality between singular symplectic varieties. You should have like variety X and variety X check. They come with some families of invariants, and under the duality, this family is small. And so this duality has been defined in some cases, but not in all cases. I'll say a couple of words about this. So what do we get in our situation? In our situation, for x check, I take the intersection of s check, this Loseu slice to O check and G check, with an important cone. That's a singular symplectic variety. And then I take x to be the spectrum of functions on this cover that we construct. And our speculation is that these two varieties are symplectically dual in a suitable sense. So the status of this is that it's a very classical result in type A. Very recently, Finkelberg, Hanani, and Nakajima established the duality rigorously for classical groups. That was the topic of Nakajima's talk. And for exceptional groups, who knows? And currently, there is no approach of how one could try to do it. But yeah, so this is kind of, yeah. So that's I think, the end of the talk. Thank you.
Any question for the speaker?
So there, if I change the cover, we get the same X, or is it different?
No.
The different, it will be a
So-
different thing.
So there is a whole bunch of cover, and you need to pick a very special one. So to give you an idea, if you start with distinguished orbit on the G check side, you need to take the Barbach-Vaughan dual orbit and take its universal cover. Or maybe even be it better, you can take the cover corresponding to the Lustig quotient of the component. So this D tilde is not quite well defined. So you have some cases.
So I'm wondering if your story of quantization via a singular Lagrangian subvariety has anything to do with the so-called brain quantization proposed by Witten, Gaiotto, Gukov, and someone else in physics.
It might, but I don't know. I'm better at physics.
Because in their story, they also need a Lagrangian subvariety so that you can obtain a Hilbert space for representation other than just a deformation quantization of the algebra.
Well, but I imagine that's on the physicsy level of rigor.
Yeah.
No offense meant for these great people.
So the symplectic duality only exists for singular varieties. So the variety, if it is smooth, then there is no such duality.
Well, okay, so here you have a very rough definition. So kind of the way how the people would say it is that there is a duality between 3D n equal 4 supersymmetric quantum field theories, and each of these theorems have two moduli spaces of vacuum called Higgs branch and Coulomb branch, and they're supposed to be interchanged via this duality. Now, I don't claim to know I know what quantum field theory is, which is to say that mathematically, this is kind of a shadow of an actual duality. You have some objects which are in duality, and they will produce these moduli spaces. Moduli spaces may be smooth. You will get something interesting. But somehow in this business, since I'm doing things conically, so I always impose positive gradings, a smooth symplectic variety would be a vector space. That's not particularly interesting.
You are talking about always talk about this Hessian by module. So you only care about here you only consider the complex group, or
So I can talk about a Harish-Chandra bimodule, the complex group case in full generality. But then I can also talk about the general real case, where the results are less complete. And the problem, I think, is that, well, I mean, it's kind of, maybe wasn't explained in great detail. So if you take, so for the real case, you talk about k orbits and k pi. And it may so happen that the codimension of the boundary of such an orbit is equal to 1. And when the codimension of the boundary is equal to 1, the story is supposed to get much more complicated. So the essential condition here is this codimension 2 condition. There are some technical conditions which hopefully can be removed without too much pain. But that's how. So in principle, with some luck, I should be able to solve this problem whenever I have a singular Lagrangian subvariety with the dimension of the boundary equal to 2, the dimension of the singular locus equal to 2, and it shouldn't care about this, Lie theorem. Maybe I should do this.
So in the complex case, you don't have this condition on the
In
co-boundary?
complex case, everything is symplectic, so all dimensions of orbits are even.
Ah, you're talking about the real dimension?
No, complex dimension, because everything is symplectic.
Ah, okay.
Just a general one. So why, if you begin with the orbit, some cover and local system there, why positivity is somehow granted?
Not granted at all.
Not granted, but
So the only thing that we know about positivity is the theorem of Davis and Mason-Brown. But everything which corresponds to canonical
But
is.
you mentioned some special cases, unitarity, pure unitarity can be proven, right?
Yeah, in that
Some
case,
special
unitarity can be proved.
So for some special parameters, your parameters, right?
So then, of course, you can deform. I think there is some interest for this in the context, of this 3D symplectic geology. There is some interest in this problem by physicists, which I should have mentioned. There are some work by Guyot and collaborators. What he told me in conversations that, that region, like this deformation region of the zero parameter, he can understand, and everything else he thinks is a miracle.
Pretty much crazy combinatorics of unitary dual, right? Some kind of regions.
Well, I mean, it's not that crazy, at least in the complex. But it's certainly complex.
Other question?
Oh, a naive question. So there's a refined dual, right? So dual to each orbit, you can dual to an orbit and plus a cover, right? To separate the.
Yep.
Yeah. So is this cover actually related to the cover that you used here?
So maybe there are two different constructions, and one can ask whether they are related. I'm not sure what is yours, but maybe we can discuss it at lunch.
Thanks.
Other question?
Like mentioning the word lunch should have some, some effect on this.
Okay, let's speak again.